start the second adaptive filter. We will go for the recursive least square adaptive algorithm now. And here we have a small change compared to the LMS algorithm. Again, the starting point is the same. We look at that how we deal with the expected value of E square n. So, in this case, instead of entirely dropping the expected operator, which gives rise to that the noise, what we called as noise in the output, what we called as that weight vector noise, we are taking actually that a summation over the time. We are taking a summation over the time for the last that n inputs, but in this case we are taking a time window lambda. Okay, lambda is the forgetting factor. Now, how it is working? That say if this is the instant 1 and now we are at instant n, the value of lambda here, which is less than 1, it would be here, and as we are going back over the window, then we are having power of n, it will reduce like this. So, in other words, what we are suggesting, that though we are doing averaging, we are giving the maximum weight to the error which is the present error and to the nearby past. As it goes further and further, the influence of it would be reducing. So, that is that main assumption of the RLS algorithm. So, now why it is actually we are taking it in this way, that because we are giving more importance to the recent value of En, it will help us to that adapt to the change in the situation. The smaller the value of lambda, this one will become, this will move actually more and more fast towards the 0, and thereby the changes will be more. But if we take lambda is very small, then there is some penalty towards it. The penalty is that the averaging also would be less, and that means again it will give actually more weight vector noise. And like the previous case, we have the En is the estimation error. So, we are having the new term introduced here, that is the forgetting factor lambda. Now, the next part or the rest of the RLS algorithm is towards the fact that we need to have an update equation of the tap weights as we have seen it there. So, let us move for that what we get here, that we get a normal equation phi n, that is a matrix, multiplied by the weight vector W n equal to theta n, where this phi n, it is a autocorrelation matrix of the reference input into the forgetting factor. When we are summing it up, we are having this forgetting factor. Same way the theta n, it is the cross between the vector of the reference input and the observed present value of I, and that the last n minus 1 values also, and again a forgetting factor is coming into play. If it is a stationary process, in that case we can take lambda equal to 1, and then as you see it will become same as our the Wiener filter. Now let us look at that how we can compute these values. We see that this phi n can be written in this way, that we can take it out the most recent contribution, that the vector Rn and transposed of the vector Rn, that the present values. So if we take it out, we are left with this term multiplied by lambda, and this term is nothing but the previous value of phi, that is the matrix phi n minus 1. So we get that update equation of phi, where if we know that the previous value, if we just compute this part and we take the multiplication with the lambda, we can update the phi n. In a very similar way, we can get an update equation for theta n, where we can compute it from theta n minus 1 and the cross between the reference input vector and the observed present value x n. So what we get, that we reduce the burden in computing. That means we need not have to start from the scratch. We can reduce that part of the computation, and for the tap weight Wn at each instance, we can compute it by multiplying the inverse of phi n, the inverse of this matrix, into the vector theta n. Now here let us look at that what is the dimension of all this quantity. See, for Wn, it is m by 1 dimensional vector, theta is again m by 1 dimensional vector, phi n is having dimension m by n, and we know that the complexity of that matrix inversion is pretty high. It is the order of complexity is actually m cube, where m is the dimension of the matrix. Okay. So this is a prohibitable an amount of computation what we need, because we have already seen that if we are taking a signal sampled at 10 kilohertz, we have only 1 millisecond time to update the tap weight Wn. So this much amount of computation would be very challenging to do, and for that we need to have a better formulation of this to make it for any practical use. So let us see that how this computation can be reduced, and rest of the LMS algorithm would be a search for that in reducing that complexity. So in an attempt for that, first we introduced one lemma called ABCD lemma. In this ABCD lemma, the goal is that the matrix what we have to invert, here in this case that phi n, say if we can divide it into few constituents in this form, that if we can represent it by A plus BCD in this form, where we assume that A is invertible, C is invertible, then D A inverse B plus C inverse, this is also invertible. In that case, we can actually write the inverse of this in terms of the inverse of A inverse and C inverse and this quantity. And how that can help? Now, if we can break it into a smaller parts which are easier to take invert, then it can reduce our computation in the inversion. To be more precise, that we recall that we have some update equation for phi with the help of phi n minus 1 plus a new term. So, here that A for the inversion of phi n, we are taking A equal to lambda into phi n minus 1, and as we have computed the previous weight, certainly we must be having A inverse. Now, for the B, we have taken it R n, C is taken 1, so inversion gives the same value, and D is again R T n. Okay. So, in that way, actually we are actually writing phi n in this form. Okay. So, once we can write it, now we try to make use of the ABCD lemma and represent phi n inverse in terms of this inverse of A, inverse of C and the other terms. So, as we write it in that form, what we notice that here we get a part that what we have highlighted here. This part, the dimensionality is 1. So, this is actually giving just a scaling, and we are taking the inverse of the whole thing. So, we can write it in a little better form, that we can write it that this part is A, that A inverse minus this is the part. Okay. And the part which is giving the scaling, we have written as a denominator. Now, we look for further simplification of it to reduce the computation further, and to do that we would like to actually make the notation a little more simple, and instead of phi n inverse we give it a new name called P n here. Okay. So, that P n we have chosen, again it is a matrix, it is nothing but phi n inverse, and another thing is introduced, that is the vector k n. And how the vector k n is chosen? Let us look at the previous page, that we have this part, this denominator, and we have this part. Okay. So, taking these part together, we are taking the k n. Okay. And by that assumption, now the phi n inverse or the new value of P n we can write in terms of that P n minus 1 and k n with the remaining terms, that the transpose of R n and P n minus 1. So, it not only that looks actually better, it becomes more readable an expression. So now, by multiplying both the sides by the denominator of the right hand side, we try to actually simplify this, and we get this new equation with Kn, and here we get two terms out of that, when you multiply with 1 we get Kn. We keep that in the right hand side, and the product of Kn and this, the first part of this term or the first term, that we take it in the right hand side, and as this one has Rn vector at the end, this R1 has their vector at the end, we take that vector Rn in common, and we can write it in this way. And what we realize, that this part what we are looking at, this is the same as the expression of Pn in the equation 7. Okay. So let us look at that, this was the expression of Pn. So using that, replacing that expression with Pn, we get a very compact form. We get Kn is nothing but Pn into Rn, where Pn is a matrix, Rn is also a vector. So that gives rise to the vector Kn. Now let us go back, that how we can compute the new tap weight, that is Wn. So Wn, we know the expression is the inverse of the matrix phi n into that vector theta n. So phi n inverse is nothing but Pn into theta n, and now if we actually write theta n, expand theta n in terms of theta n minus 1, and the component that Rn into Xn, that here we can actually, if we go back, that we will get this equation, that theta n is nothing but that theta n minus 1 lambda times plus Rn into Xn. So using that, we have expanded it in this way, and now in the next step what we do, we actually replace Pn, okay, the Pn in terms of Pn minus 1 and the other term with Kn. So we put that. So we have now 3 terms, and out of that what we get, that the first part, that this one looking at this equation Wn, that we get, it is nothing but Wn minus 1, and we have 2 more terms here, okay, involving Wn minus 1, which we know, okay, that is the good part of it. What are the things we do not know? That is Pn, we need to compute that. We know the value Pn minus 1, we do not know Kn. These are the things we need to update to get Wn. So we look further for simplification, and in the next step we start from there where we are. We are there in the last page, and from that expression what we do, we get the last part, that Kn equal to the matrix Pn into Rn. So, we are replacing this part with Kn. Now, as the second and the third term both are having Kn, in the fourth line we are taking them Kn in common and we are writing this term. And if we look at this term, that it is very similar to the error equation. Okay, that the only change that in case of error equation, that W instead of n minus 1, it would have been Wn. In any case, that for this term we are replacing it with a new name, that is called alpha. Now, if we at the beginning start with that initialize with 0, then we can write that alpha is nothing but that xn minus the dot product of the reference signal and the previous tap weight, that means the tap weight at the previous instance. Okay. So, we can change their order because they are just the dot product, and because we are using the tap weight of the previous instance, it is called a priori error. Instead of error, we give a new name for it, what we call as a priori error. And here it would be interesting to note that if the process converges, that means there is no change from n minus 1, or there is hardly any change from n minus 1 to n for the tap weight, then this a priori error would be same as the error En. Okay. So, in case of convergence, that is what we would get. Now, taking the previous equation, that we would like to have a recursive equation to estimate the tap weight, and for this particular application of adaptive noise canceller, in short ANC, that after the convergence, the alpha n, it will be same as the En. Okay. So, that is what we note, and the equation what we have seen in the previous one, that this is our update equation what we get. Now, out of that, actually what is the thing that is difficult to estimate, or we need to take effort to compute, that is only Kn, because Wn minus 1 is known, computation of because Wn minus 1 is known, computation of alpha n is also trivial. The only cumbersome thing is the Kn that we have to compute to get the estimate or the new estimate, that is Wn. So, with this we complete the part of RLS filtering. Thank you.